this week, today, we're going to finish talking about trusses, and it's not going to be as overwhelming as Friday's content was. I know it's a lot to process with all the matrix formulation and everything. Today's lecture will be more focused on intuitive truss analysis, method of sections included in that, and finding zero force members, thinking about stability, things like that. So that's today's focus. And then we're going to shift gears and talk about some other types of structures later this week. So cables and arches on Wednesday, and then we'll get into shear and moment. Specifically, we're going to focus on shear and moment for frames, since you guys have done shear and moment plenty of times before for beams. There will be a little bit of a recap on the basics, and then we're going to just start applying it to frames. And then next week, we'll get into elastic curve, and then we'll start talking about finite element analysis. So I think one of the things that makes this class challenging is that there are just so many different topics that we have to touch on, right, that we have to cover. And it's really mostly an ABET requirement. Like, we have to cover all this different material, which I do think makes it a little bit challenging. And I know that's not unique to this class. There are other classes that are similar in that regard. But as far as the structures classes go, I think it's one of the most widespread classes, topic-wise, if that makes sense. So keep that in mind. We're not diving too deep into all of these topics, but we do have to cover a lot of different things. And that applies throughout the class too. Like, even when we get into load designation, we've got a lot of different topics in there as well. So, all right. So one thing I would like to point out, all right, so as a refresher, this is the first homework problem in this week's homework, which is due a week from today, all right? So you do have a bit more time for homework 3. So this first problem is all about what we did on Friday, right? The idea is we're going to apply a method of joints, which is something that you all have done before. So you're all familiar with that approach. And we're going to structure it so that we can streamline it and solve for multiple different load cases at the same time, right? So you remember that from the example we did. And if you follow the process that we did in the class example, that's exactly what will get you through this assignment. One thing I would like to point out, and I added this note to the bottom of the page for you. It's not in the D2L document, but just to show you in class. All right, the textbook shows a slightly different approach. So I want to show that to you real quick. Let's switch over to the doc cam here. All right, so in the textbook, here's section 7.9, and it starts off the same, right? So it starts off by writing the joint equilibrium equations in general terms, not, in general terms, actually, they do account for the specific load case, all right? So that's one thing that if you want to follow the method outlined in the book, just keep that in mind to apply it to this assignment, since we're going to solve multiple load cases at the same time. Instead of, for example, saying negative 30 kips here, you would have, something to represent an applied force in the y direction, right? And you would have to add something to represent an applied force wherever there's not a reaction force in the equation, all right? So you still want to have one external force for each equation, okay? What the book then does, it does not apply partitioning, all right? So the approach that the book takes, you just solve one matrix, right? And you just solve for all the unknowns at the same time. And that's a valid approach. If this makes more sense to you and you would like to use that for your homework problem, we'll accept that. Just I would ask that you make a note in your assignment that you're using the books method instead of the in-class method. That'll help us just understand and follow your work when grading, okay? But what the book does is it separates, right, all of the known forces, all right, are isolated on one side of the equation. So this would be your F1x, F2x, right, F1y, F2y, F whatever, you know. So it would be all of the terms that you had to represent possible applied external forces, right? So they're using A, B, C, not 1, 2, 3. All right, so this would be maybe FAX. No, actually, these would both be zeros because you have reactions there. All right, so if you have a reaction, then you don't have an applied force. So all of those would still be zeros if you were to apply this as solving simultaneous equations or simultaneous load cases. This would be FBY, all right, FBY, there's got to be an FCY in there too. So one of these would be FCY. And then all of the unknowns are in that column vector matrix, all right? Once you expand it to include multiple load cases, of course, it won't be a vector anymore, but when you set it up, it looks like a vector. So in that way, you can solve for all the unknowns at once. I prefer the partitioning method because it's going to set you up for getting used to applying that partitioning when we do finite element analysis. So you're going to be using partitioning a lot through that. So I recommend that you use the approach outlined in class, but I just wanted to point out in case this does make more sense to you, you're welcome to use this method for homework 3. All right, questions? Yeah?
Do you want us to turn in our work from Excel as well?
It's not required.
Okay.
You're welcome to, but it's not required. Yeah. Right.
You still want the steps written by hand, though, right?
Right.
That actual math we can use.
Yeah, exactly. Yeah, you can. Yeah, please use your calculator or Excel. I recommend Excel. So use something to do the math, but just write out the process with the results and everything. Yeah. All right. Other questions? Okay. All right, so, right, so then the second page of the homework is tied to things we'll talk about today. All right, so this problem is going to be a good method of sections application and observation, all right, identifying zero force members, things like that. Got a hint in there for you. And then third problem should be, all right, so these are book problems. They should be pretty short. These are just evaluating determinacy and stability, and then that's these three. And then this last one is identifying zero force members. So we've already talked about determinacy, so today we're going to talk about all the other stuff. All right, so first up, special types of joints. This worksheet or this handout is pretty handy to refer to whenever you are considering truss analysis. And, you know, it's nice to have, but once you get accustomed and more comfortable with analyzing trusses, you'll find that you won't really need to refer to this handout anymore, right? It'll just come naturally to you. Probably the most useful ones out of this sheet are the first two. So this type 1 and type 2 joint. In the book, they call these the 3-member rule and the 2-member rule. All right. So these are great for identifying zero force members. Essentially, it's right what you see here, right? If you have the 3-member rule is you have a joint, that's joint A. It connects 3 members. If 2 of those members are collinear, meaning they align on the same axis, and if there's no load applied at that joint, then the 3rd member is going to be zero force, right? The 2-member rule is if you have a joint that connects 2 members and there's no load at that joint, then both of those members have to be zero force, okay? The rest of the types just go through some, useful items or pieces that are going to be, help you develop your intuitive understanding of trusses, right? So if you have 4 members connected at a joint and these 2 are collinear and these 2 are collinear and there's no load, then you can understand, right, without doing any calculations that these 2 are going to have the same internal force and these 2 will have the same internal force as each other. All right, and then similar throughout the rest of that. So now getting in a little bit more to truss behavior. All right, if you've been keeping up with the textbook reading, you already know some of this terminology, but essentially with a truss, we refer to members as being either part of the top chord, bottom chord, or a web. So the top chord, right, is what we see here. All right, there's your top chord, here's your bottom chord. And then the web members can be vertical or diagonal, right? So they act as the link between the top and bottom chords. Now this truss example is simply supported, right? You have a pin on one end and a roller on the other. So a beam analogy would be a simply supported beam. If we have a load acting downward on this truss, all right, that's similar to a load acting downward on a beam, simply supported. That beam would deflect like this, where you would have tension in the bottom fibers and compression in the top fibers. Similar to that beam, all right, your bottom chord will be in tension, and your top chord will be in compression. All right, and the web members could be either tension or compression depending on how they're configured. Of course, if the load is reversed, right, your bottom chord will be in compression, top chord in tension. If you have a truss that is configured like this, all right, with the supports on the side like that, this is no longer analogous to a simply supported beam. All right, so your top chord is what I highlighted in yellow there. If you were to apply a force acting downward on this truss, all right, the behavior would be analogous to a cantilever beam with an applied load acting downward. All right, so in a cantilever beam, you're going to end up with compression in the bottom fibers and tension in the top fibers under such a load condition. So now your top chord is in tension. All right, so now we're going to get into zero force members, which I think is always a fun part of truss analysis because once you start identifying zero force members, sometimes you see even more zero force members, and then you can really sometimes whittle down a large truss to a very simple problem to solve, right? So what is the purpose of zero force members? If they don't carry force, why even bother? Yep.
They could support like wind load or snow load.
Right. They may be necessary to carry force in other load conditions, right? So as you know, we have multiple different load cases that we need to consider for all of our structures. So members that are zero force under one load case may be necessary to carry load in other load cases. So I'm going to note that they're needed to carry forces under alternate load conditions. But what else are they good for? Stability, right. They may be necessary just to provide stability. So even if there aren't any load conditions that that they're going to be carrying force for, they may just need to be there to stabilize a joint, for example. Anything else? Maybe a non-structural reason? Yeah, aesthetics. And then one last point, they can provide redundancy in the case of, this is for indeterminate beams really, so you may want to have more than one load path for a given set of loads. And that helps too if, maybe some members become compromised for some reason, then you have an alternate load path. All right, so let's consider this truss here. And right now there aren't any loads applied, but let's say that we have a load applied at joint G. All right, and this truss is determinate, all right? And we'll talk about stability later, but I will confirm that this truss is also stable. So how many zero force members do we have under this load? Take a second and think about it. See how many you can identify. Anyone think they have a count, final count? Yeah?
I'm gonna say
8, okay. Anyone have a different count? 2. All right, 2. 2. 2. All right, somewhere in between.
4.
4, yeah. That's right. Was that a guess or?
No, I figured out where I
You
wanted.
figured it out? Okay. Yeah, 4 is exactly correct. So I'll show you where they are in a moment. So there's 4 zero force members. All right, so would you like to tell us where you got some?
HB, BG, GD, and DF.
Right. Yeah, so we can readily identify HB and DF using the 3-member rule, right? I think it's the type 1 joint. So those are zero force members. That's right off the bat. Is that what folks saw when you said there's 2? Yeah, so that's a great start. But once we identify those 2 zero force members, then suddenly joints B and D also become 3-member joints with respect to identifying zero force members, right? So even though, of course, there are 4 joints or 4 members at that joint, if you identify a zero force member, you can delete it from the truss for the purpose of analysis, right? So once we do that, then we can identify B and D as zero force members as well, or BG and DG, right?
If the force is applied at that joint, why doesn't it pull BG and DG in tension?
Great question. So that's because you have CG, all right? So the force will just be carried completely by CG. Yeah, I know, it's a little bit counterintuitive there, right? And this is where identifying zero force members can get really tricky and you can tend to overthink things. But if you remember the 3-joint rule and the 2-joint rule and think about, the joints, both of the ends where that member is, all right? So if we were to add add a force at D, how do you think that would change things? How many zero force members would we have now? We would have 3 actually. All right, so we can still say, right, it doesn't affect what's going on at joint F. So we can still say that FD is a zero force member, but now we cannot say that DG is a zero force member, right? Because even though once FG is zero force, this is your three member joint, right? But now there's a force applied to it. So DG is the only one that would be affected by a force at G being added, or a force at D being added, right? Out of those 4 zero force members. So yeah, so it takes a little bit of practice, and it's not always obvious or intuitive, but keep referring to the, that previous sheet, and you'll get the hang of it. So under this load, right, with the force acting downward on the bottom chord, the top chord, right, which is A, B, C, D, E, that top chord will be in tension or compression. Right. So A, B, C, and C, D, E are in compression. So the zero force members under this load are really just there to provide stability to joints B and D to help prevent buckling in that top chord. So buckling is a concern that we have to think about whenever members are in compression, right? All right, so on the next page, you'll get another chance to practice identifying zero force members here. So look at this first truss. Take a minute. How many zero force members can you find? Anyone think they got it?
I want to say just 2.
Just 2?
6.
6? 3? 3? 2, okay. Say 4, all right. So you're closest with 4, or 6 is closest to, there's 5. Yeah, so which 2 are probably the easiest to spot right off the bat? CE is not zero force because you have a force at E, right? Yeah, so ED, for me, the 2 most obvious ones would be ED and CD, because you have that two joints, or 2 members at a joint, right? No load at the joint. Now, once those 2 are identified, where can we go from there? HB, did I hear that? Yep, HB, using that 3-member rule. And this is where it starts to get a little tricky. You have to get a little creative in your thinking. And it brings in sort of another rule that I'll write out in a moment. But what's the fourth one that you found? BF. Okay, so BF is not zero force in this case. Not FC either.
AG.
AG, yeah. How did you find AG?
Because the reaction on the bottom has to be only in the X.
Exactly, yeah. So if you look at joint G, right, and you draw a free body diagram, you have GF, AG, and the reaction. All right, so just by looking at it, if you sum forces in Y, AG has to be 0, right? So using that same strategy, is there another one that you can identify?
Yeah.
Very good, yeah, EF. So by the same logic, if you look at joint E, you have applied load P, unknown CE. We already identified ED as 0. And so from summing forces in X, EF has to be 0. So here I'm going to write down one more trick. All right. If you have a joint, let's see, how do I want to put this? If you have a joint with 2 members, and essentially after you eliminate, right, after eliminating other zero force members, and you have an applied load where the resultant of that applied load is collinear with one of the members. Then the other one is a zero force member. So in another example, all right, if we use this same truss with another load consideration, all right, if you had a load applied at joint D that was collinear with CD, then CD would not be zero force, but ED would still be zero force in that scenario, all right? All right, questions? Want to try one more? All right. All right, so this one down here. What do you think?
5.
5? Any others? Okay. So the only force applied is at B. Over on the right side of the truss, looking at joint D, all right, we can find DF as 0 force. Once we identify that one, what's the next one we can pick out? Yeah, so once DF is the 0 force, then joint F becomes that type 1 joint, so CF. And then, are there any others after that? So we can't do FE because the reaction force at E is not collinear with either of those two members. Yeah. So this is actually it. It's just those two for this truss under this load scenario. All right. So I'll say you have type 1 at D. So DF is 0. And then F is type 1. So CF is 0. All right, so you'll get another chance in your homework to think through some of these and apply it. I think it's kind of fun. I don't know. Anyone else enjoy it? Yeah. All right. All right, so now we got method of sections that we're going to discuss, and I know you've seen or you've been introduced to method of sections, but maybe you haven't applied it as much as method of joints. Does that sound accurate, or would you say you've got a pretty solid grasp on method of sections too? Okay. A mixed bag there. All right. So method of sections, all right, again, this is a method where you get to be a little bit creative, a little bit strategic. Identifying 0 force members either before, during, or after can be very beneficial. Or I guess before or during, right? Not necessarily after, but we're going to look at this example. And here we have a truss that is simply supported at A and I. And we have these two panels in the center that have cross-bracing diagonals. All right, and it's given in the problem statement that or I guess it's in the solution, all right? So it's saying that the assumption that cross diagonals are light applies in this scenario, all right, and will not carry compression. So we're going to use the method of joints to first identify which of the cross diagonals are going to be active in tension under this load case. So we're first going to make a cut through one of the panels. I'll go through this one here. All right, I'm going to call that section 1. So then we look at the right side of that section and draw a free body diagram. This is done also after computing the reactions, by the way. All right, so on the entire truss, you've got 2 applied loads. You can apply equilibrium to calculate the reactions at the 2 supports. So then knowing the reaction at I and looking at this free body diagram, we can tell that the net applied load on this free body diagram is 60 kips, all right, but more importantly, the direction is downward, all right? So that's all we really need to evaluate intuitively which of these cross-diagonal members is going to be active in tension, and it's going to be EK, since it's the only exposed force that can oppose the downward net applied force, right? Or I should say net external force, because that's not applied, it's a reaction. So So we get EK, and here's the actual equilibrium calculation to show the value, all right? EK is 84.8 kips in tension. And so then it follows, since there's no additional load applied between the two panels, if we were to take a cut through that panel, we would find similarly that DL would be the active one in tension as well. All right, so then the other part of this truss that we're going to look at is finding the force in member JH, all right? So that was the other part of the problem statement there. So in order to do that, we're going to take a second cut, and this one will go through the panel that includes member JH. So here is the second free body diagram. That cut exposed 3 unknown forces, all right? And none of these are the light version of diagonals that we can assume only carry tension, all right? So we can't apply that here. We have to assume they can both be tension or compression. But what is convenient about this cut is that 2 of the unknown forces pass through, their line of action passes through point F, all right? So with that in mind, we can strategically choose to sum moments about point F and then directly solve for the force that we want in JH. Now that's not the only way to go about finding JH from this free body diagram, right? You can also do some forces in X and some forces in Y, solve, and then some moments about a point, right? Because you have 3 unknowns there. Or you might look at joint I, right, and use that to find IJ, and then from there go back to the whole section and then find the ones that you want. But the most efficient solution would be to recognize that you can take advantage of this point that these 2 members, their line of action passes through. Now it's important to remember, it doesn't matter if the actual member is attached to that joint. It doesn't matter if the actual member passes through that joint. What's important is that the line of action passes through it. The point where you sum moments about doesn't even have to be on the truss. If, usually for convenience it is, or on the structure. But sometimes you might find a truss or a structure where, you can find a point outside of it that a bunch of members pass through and some moments about that point to eliminate those unknowns. All right, so using that approach, again, you can find that FJH is equal to 56.6 kips in tension. Questions? All right. Next example. Here we have a truss that has a different type of notation. So here, this is one way that truss joints are numbered, where you use U for upper on the top chord, L for lower on the bottom chord, and then any intermediate joints would have an M. And then you have those values numbered roughly according to the panel that they're associated with. It's not really that important, how you number your joints, just as long as, you're clear in your joint numbering and you're consistent in your communication throughout your solution. So we're looking in this example for the force in member M to L3. So that is this member right here. And this solution is going to require 2 cuts to get there. Because if we cut through this panel to expose M2L3, we can't do that without cutting through 3 other members at a minimum, right? And so if we do that, we would have too many unknowns. So we need to make another cut first that will allow us to eliminate one of those unknowns. All right, so we can do that. One way would be to make a cut like that. So I'm going to call that section 1. And here's the free body diagram of section 1. Now, what's convenient about this particular cut that I chose is that the one that we want in this free body diagram would be one of the ones that would help us out with the second cut, right? So the other two happen to pass through this point U2. So we can make use of that, some moments about U2, and then solve directly for the F2L3. All right, so we get F2L3 is equal to 30 kips in tension. Then we can go to this second cut. All right, and here's the free body diagram for 2. Now we know F2L3 is equal to 30. And we have these two passing through U3. So we can sum moments about U3 to directly solve for M2L3. Right. So method of sections takes a little bit of extra thought and strategizing. Right. Questions? Okay. All right, so we have a few minutes left. We'll talk about stability. All right, so as you know, you have this equation to evaluate internal determinacy. And right, if m is less than 2j minus r, we've already covered that, it's unstable. All right, so that's one way to confirm that a truss is unstable. However, if m is equal to 2j minus r or greater than 2j minus r, right, that tells us whether it's determinate or indeterminate, but it doesn't necessarily mean stable. So another way to evaluate stability is by imagining the deformed shape. And this is more of an intuitive assessment. So as we've mentioned before, right, if a structure can experience motion without deformation, that is what we call rigid body motion, right? And that is the sign of an unstable structure. So rigid body motion is what you dealt with in eGen 202 dynamics, right? We saw that all the time. But now in structures where we're sum of forces is equal to 0 instead of MA, that rigid body motion should not exist. All right, so that's visually summarized here, where you have a panel, all right, that is unstable. So if you add a lateral force to that panel, it would deform, it would move, right, like this without deforming. So you would still have, right, the same lengths. Those lengths wouldn't change. Whereas if you add a diagonal to stabilize that panel, and then under a deformed load, right, it cannot deform, or it cannot move without that diagonal member stretching. All right, so that diagonal member would be L plus delta L. The side panels won't necessarily deform, all right? They might, it depends on the exact load applied. But it's impossible for that panel to move in that way without that diagonal member stretching or compressing, right? So your best bet with regards to stability is to look for triangular panels, all right? And if you don't catch an instability in a truss configuration, when you model it or when you analyze it using method of joints or method of sections, maybe not method of sections, that might not reveal it, but method of joints definitely would expose the instability because you would just run into endless problems trying to solve it. You would, there would basically be infinite solutions to an unstable truss. So what that looks like in terms of our matrix assembly of method of joints that we talked about on Friday last week. All right, so if you have your matrix equation the way we did in class, where you have all your external forces on one side and then you have the geometry coefficient matrix times your internal forces, which are all unknown, then you partition it, all right? If you evaluate that first partition, which should have a size 2j minus r rows by m columns, remember, if that first partition is square and the inverse exists, then it is stable, right? Not only is it stable, it is also determinate. If it's square but the inverse does not exist, then it's unstable, right? It would be determinate because it's square, but it's unstable because you can't take the inverse. If it has more columns than rows, right, it would be a rectangle that's longer than it is tall. That would be an indeterminate truss. All right, because the number of columns represents the number of members, and that's greater than the number of rows, which is 2j minus r. And then flip side, if you have more rows than columns, it's unstable. And that's just your m is less than 2j minus r. And then the last note down here is just a comment on indeterminate trusses. So essentially, if you have an indeterminate truss, if you can remove members or a member, however many you need to take away in order to make that truss determinate, if you can do that and it's still a stable truss, then the indeterminate truss will also be stable, right? But if you model your truss in a program, that will always catch the instability. So it'll just spaz out at you and say, no, we can't model this, your truss is unstable. Which you'll find out when you do visual analysis. Tony's nodding. Yeah. Tony knows from Steel Bridge. Yeah. All right. So that wraps up our truss discussion. Any questions? If you're excited about trusses and you want to get involved in Steel Bridge, talk to Tony.